and from that infer, what are the losses or the collection efficiency of the virtual impactor. So we did a little bit of an estimation, how much mass can we hope to measure, and so in this case, we're actually measuring a nanograms change in the mass of the filters, which is about 3 orders of magnitude smaller than you can with normal gravimetric methods, right? So this actually allowed us to, or this is work in progress, where we have collected some data, and actually allows us to try to validate or verify the cut point of the virtual impactor. We're still analyzing the data, but so far we can tell that at least bigger particles, there are more losses in the virtual impactor than for smaller particles. So there is an indication that seems to say that we're around, the cut point is about right. We're still analyzing the data, but at least now we have one method that works, on this low flow rate. So that's essentially one of the challenges. The other thing which is very interesting coming out of this device, and again it has to do with the reduced dimensions, is it has to do with the thermophoretic precipitation or precipitator. So we analyzed what is the sensitivity of our device with respect to the heater, right? The heater temperature, and also the flow rate through the device. And so if you think about it, just from first principles, the precipitator should be agnostic to the flow rate, just because if you're pulling more air through your below your heater, right? There's essentially higher velocity. Okay, the thermal velocity should be roughly the same. I mean, we don't anticipate to be cooling the heater down any significantly, right? So okay, we have more particles, but they clear the space underneath the heater quicker, right? So basically, it shouldn't really matter. Well, turns out there is actually high sensitivity to flow in our device. Okay, so if we turn up the flow, it actually works